All right, good afternoon. All right, so how are you guys doing today? Let's see, we got some extra people in Hopi that want to learn calculus today, it looks like. Very cool.
I like your tie, Strong.
Oh, thank you. Spider-Man rules. Um, so, um, so how did your baseball game go, Tobias?
We lost.
Oh man. Well, so yesterday we uh, went over part of 9.1, well 9.1 and 9.2, the last part of 9.1, and so today we're going to go into 9.3. So applications of differential equations. Okay. So if you want to get out your 9.3.
So I was talking to Mrs. Townsend, and she said she doesn't have any printouts, and I looked on Moodle, and I didn't see any like printouts for the guided notes.
For
So I don't
9.3?
Yeah, I don't know if my Moodle was messed up or what, but like it didn't have anything on 9.1 except for videos or something like that. Or not 9.1, but chapter 9.
Let's see.
But Mrs. Townsend said she had 9.4 and 5.
But not 9.3?
Yeah, she said, because I was asking her like, what if you sent her anything, and she says I have 9.4 and 9.5, but no 2 or 3. And I said, well, all I have is 9.1, so.
Let's see here. Well, I don't know if I can check my email quickly on this computer. Let's see. Nine one, 9.2, 3, 9.4. Yeah, I know I emailed them to her. But you know what? I did it during spring break. So it might, got it lost in the shuffle. Let me see if I've got it posted on the website on the Moodle. Because I can easily put it up there. See, there it is. Right. Oh, it's not. It's not in PDF form. All right. Well, we can fix that. Okay, so do you see it now?
Well, I don't have a computer, but I can go get on one real quick.
Okay. Well, yeah, and just see if she can print it out for you.
Okay.
Okay.
I got it.
Okay, great. All right, well, let's go ahead and start then. All right, so Jada, do you have the 9-3 guided notes?
Yes.
Okay, good. All right. So let's go back to that. Okay, so
Before I forget, I'm not gonna be here tomorrow because I have another baseball game.
okay. All right. Well, hopefully we can finish this section because really the last part of this is the part that you really need to be here for. And I know I wish Weston was here, but he let me know that he was sick. Okay. So hopefully he'll be better tomorrow. So anyway, you're gonna be here tomorrow, Jada?
Yeah.
Okay. All right, good. All right, so this is on applications. Now, the first part is actually a review because what I'm trying to get across here is that, in 9.2 we learned about how to solve the regular linear equations, the differential equations. But I want to remind you that if they are separable, if you can separate the x's and the y's, then this is the easiest way to do it. Not the way that we did yesterday. But in this section, we're going to do them both ways. But I want to start with the easier way. So again, separable equations are those where the dy and the dx can be split apart with the x's on one side and the y's on the other. And so you rewrite it, separate the variables, and then you integrate both sides. So that's basically what you do for those. Okay. All right. So let's see if you can remember how to do this. Okay. So see if you can separate the x's, put the x's on one side, the y's on the other, and then integrate both sides. So let's just see if you can remember how to do this. Okay, so hopefully you got to this part where you get the y's on one side and the x's on the other side. So this is what we mean by separation of variables. Okay, and then you integrate both sides. So Jada, what's the integral of y squared dy?
Would it be um would it be y or to the third over 3 or
Yes,
yeah.
it would
Okay.
be. Okay, and then what's the integral of 5x? So you
Would it
add
be
1 to the
5x?
exponent
Oh, f5x squared
over
over 2.
2, because then you divide by that. And then you have to put a plus c on one side or the other. Okay? That's it. That's the answer. So that's definitely easier than what we were doing yesterday. So you just want to remember how to do the separation of variables. Okay?
Mr. Strong,
Yes.
the camera is on your chair and we can't see you.
Oh, I'm sorry. Sorry, I got a little excited there. Thank you. Okay. All right, so this is another application of differential equations that where we come up with a formula. All right. So this is a separable differential equation representing exponential change. The solution to the equation with initial condition v equals v sub 0 at t equals 0 is, and so this is a formula that we get through solving a differential equation. So v, which is the velocity at any time t, is equal to the initial velocity v sub 0 times e raised to the negative k divided by m times t, where k is the rate of change, m is the mass, and t is time. So in the next problem, we're really not going to be solving differential equations. We're just going to be plugging into the formula that we get from differential equations. So it almost feels more like an algebra problem than a calculus problem. But this result, this application, this formula is from solving differential equations. Okay, so let's go through how to plug it in. Okay, so it says for a 192-pound ice skater, the K is about 1/3 slugs per second. Okay, so a slug is actually a unit of in the metric system. Okay, but it's a unit of mass. Okay. Now the mass of the ice skater is the weight divided by gravity. So 192 divided by 32. Oh, this isn't metric. This is the English system. So 192 divided by 32 is 6 slugs. How long will it take the skater to coast from 11 to 1 foot per second? All right. Now, so using this formula, we say, okay, so the velocity, see, we want to know when the velocity is 1, how long did it take? So the initial velocity is 11 and the current velocity is 1. So we're going to plug in a 1 here and 11 here. And then we have e to the negative. All right, so it says k is 1/3 slugs. So we do 1/3 divided by, and then the mass is 6 slugs. So 1/3 divided by 6, and then times t. So now we've plugged in, so now we have to solve for t. So the first thing is to deal with this 1/3 divided by 6. With a complex fraction, it's easier to think of it as 1/3 times 1/6, which would give us 1/18. The other thing I did in this step is divide both sides by 11. All right, now I'm trying to solve for t. So what do I do there to solve for t? What's my next step?
Would you take the natural log of both sides to cancel it?
You sure would. So then you'd get the natural log of 1/11 is the natural log of e to the negative 1/18 t. And then the natural log and the e cancel and your exponent comes down. So you get the natural log of 1/11 is negative 1/18 t. So then to solve for t, what would I do?
Multiply by negative 1/18.
No, you either divide by negative 1/18 or multiply by negative 18.
Yeah, yeah.
So that's what you meant? So then that's what you would put in the calculator. And so then your answer is going to be 43.162, and that's seconds. So the ice skater's going along, and then all of a sudden he stops and then just glides, glides to almost stopped. And that's how long it takes to go from 11 feet per second to 1 foot per second. So as he's slowing down, that's how long it takes. Okay? All right, now what I'm going to do is give you another formula, sort of a part 2 of the problem, and have you do it. Okay? Another formula that's a result from linear equations, from differential equations. So to find out how far the body will coast, so how far the skater is coasting during those 43 seconds, you use this formula, d equals v sub 0 m divided by k, where d is the distance the skater's going, v sub 0 is the initial velocity, m is the mass, and k is the rate of change. Okay, so you got that written down? Okay, so now it says, how far will the skater in example 1 coast before coming to a complete stop? Okay, so here's the information back in example 1. So now you're going to try to find D. All right, so Tobias, do you have it?
Yeah, I got 198. Would it be feet?
Yeah. 198 feet. Good. All right. So Jay, did you get that?
Yeah.
Okay, wonderful. Okay, so that's another application, is just kind of using formulas. All right, now, the problem with these exponential growth problems is that in the real world, different things happen. Like if you did exponential growth, like earlier in, we did problems like with population growth, but in real life, there's things like limited resources, fluctuation in growth, social conditions like war, famine, that they affect these things. So we have what we call, the formula is kind of like our theoretical model, but then in real life, it doesn't always work out to be exactly that way. Okay. All right. Okay. Next, another application of differential equations is what's called orthogonal trajectories. So, and it sounds all difficult, but it's really not. An orthogonal trajectory of a family of curves is a curve that intersects each curve of a family at right angles or orthogonally. So what we're talking about is perpendicular. Okay, orthogonal is just, we use the word orthogonal because it could be perpendicular in 3 dimensions. Okay, so says on an orthogonal trajectory, the slope of the tangent line at a point must be the negative reciprocal. So if you were to say, all right, let's say that this blue line here has a slope of -1/2. Then what would be the slope of all of these red lines if all the red lines are parallel? So let me ask the question again. If the slope of this blue line is -1/2 and it's perpendicular to all of these red lines, what would be the slope of all the red lines?
Would it be +2?
+2. Okay, so that's really the important thing in all this, is that perpendicular or orthogonal lines have negative reciprocal slopes or opposite reciprocal slopes. Okay, so again, the question itself sounds like it's harder than it really is. Find the orthogonal trajectories of the family of curves xy equals a, where a is not equal to 0, is an arbitrary constant. Okay, so you have xy equals a. Well, how do you find the slope of a curve? What did we do in Calc 1 to find the slope?
Would you take the derivative?
Take the derivative, okay? So we're going to take the derivative of this. So the derivative of xy, we're going to have to use the product rule and say, okay, the derivative here is, the derivative of x is 1 times y plus x times, okay, now when we take the derivative of y with respect to x, we've got to add in the dy dx. So x times dy dx equals 0. So the derivative of a constant is 0. All right, now, to find the derivative, that's the same thing as dy dx. So we're going to solve for dy dx. So we subtract y and then divide each side by x. So dy dx, that's the slope of the tangent. So negative y over x. So what would be the slope of lines that are perpendicular to that?
Positive x over y.
Positive x over y. So that's the answer. Those are the slope of the orthogonal trajectories or orthogonal projections. Okay? It just means the perpendicular lines. So you flip the fraction, change the sign, and so you get x over y. Okay? So in these problems, there's really two steps. So one, you take the derivative, and then you do the opposite reciprocal. Okay? So, okay. So let's see if you can do this one. All right, so Tobias, what's the derivative of kx squared?
I'm not gonna lie, that K is throwing me off. I cannot think right now, and that K is just really messing with my mind.
So just think of k as a constant, like 5. See, what would you do if it was 5x squared? What would be the derivative?
It would be 10x.
Right, so you just bring the 2 in front, so it would be 2 times k times x.
Oh, okay.
Okay? All right, so Jada, what's the derivative of y squared?
2y.
Okay, keep talking.
2y.
2y
Oh, dy dx.
dy dx, because whenever you take the derivative of y with respect to x, you got to throw in the dy dx. And then the derivative of 1 is 0. Okay, so now you have to solve that for dy dx. So get dy dx by itself. All right, so Tobias, when you've solved for dy dx, let me know.
I got negative 2kx over 2y.
Okay, so you subtract the 2kx, divide by the 2y, and then you can cancel the 2's. So then you end up with negative kx over y. Okay, so that's the derivative or the slope of the tangent. All right, so then Jada, what would be the slope of the orthogonal trajectories, or all of the perpendicular lines to that?
Y over kx.
Y over kx. So you flip the fraction, change the sign. So the slope of the orthogonal projections or orthogonal trajectories, just a fancy way of saying the perpendicular lines. Okay. All right. So those are some applications that you can find with these differential equations. All right. So now the last example is going to take us the rest of class, and I hope we can finish it. But if we don't, we don't. But the last example is what we call a mixture problem. Okay. Now, with a mixture problem, we're going to look at things like the rate in. So we're going to have a container, and we're going to look at the rate that something flows in, the rate that something flows out, the rate of change in the container. These are going to be some of the things that we look for here. Okay. So we'll come back to that. All right. So here's the problem. It says, is this the same one? Okay, it says in an oil refinery. Okay, so this is different than the one that's on your the practice problem. So I would recommend that you you take notes on this as I go through this example. Okay. So don't worry about writing down the problem is in your book, but as far as, the key ideas as we go through. And so what I'm going to have you do is actually try to work the practice 3, which is very similar to it. Okay. And so try to do that for tomorrow. So it says in an oil refinery, a storage tank contains 2,000 gallons of gasoline that has 100 pounds of an additive dissolved into it. So you might not know this, but gasoline goes bad when you store it. And so there's different additives that you can add in gas to make it not lose its potency. All right, so it's got 100 pounds of an additive dissolved into it. In preparation for winter weather, gasoline containing 2 pounds of the additive per gallon is pumped into the tank at a rate of 40 gallons per minute. The well-mixed solution is pumped out at a rate of 45 gallons per minute. How much of the additive is in the tank 20 minutes after the pumping process begins? Okay, so that's a pretty complicated problem. It's pretty involved here. Okay, so let's kind of see if we can look at a picture here. So here we have our tank with 2,000 gallons. All right, and then we already have 40 gallons per minute is getting pumped in, containing 2 pounds per gallon of the additive. But then 45 gallons is getting pumped out. So 40 getting pumped in, 45 gallons getting pumped out, containing Y divided by V pounds per gallon. We're going to have to figure out what the Y and the V is. Okay. Now, okay, so the V, the volume in the tank at any time. We start off with 2,000 gallons, but then we're adding 40 gallons per minute. So that's why it's plus 40T. So every T we're adding 40 gallons. But every minute we're pumping out 45 gallons. So we're adding 40 gallons and subtracting 45 gallons per minute. So if we simplify that, So 2000 minus 5t, that's the amount in the vat at any time t. Okay? All right. So the rate out, okay? So the rate out in general is, okay, so the y of t, how much the additive is in the whole volume times the outflow rate. That's how fast we're pumping out the additive. All right, so that's y divided by, and we said the v of t was 2000 minus 5t, and the outflow rate was 45. So that simplifies to 45y divided by 2000 minus 5t pounds per minute. So we're talking about the amount of just the additive. How fast is the additive flowing out? Okay. Now the rate in, it's 2 pounds per gallon as the additive times 40 gallons per minute. That's how fast we're pumping the additive into the vat. So that would be 80 pounds per minute. That's how much of the additive, the gasoline additive, we're adding in. So the rate of change in the container is the rate in minus the rate out. So if we take these two problems, so the dy dt, that's the rate of change. So that's 80 minus 45 divided by 2000 minus 5t. And then y sub 0 equals 100, that's our initial value. So that's saying before we start pumping in or out, we have 100 pounds of the additive in the vat, in the container, to begin with. Okay? Any questions so far? Okay, now, let's see if we can. Okay, so that was our rate of change. And so what we're going to do then is think of this as our differential equation that we're going to solve. So this was the standard form. So this is our differential equation to solve. All right, so now Tobias, if you haven't seen yesterday's video, this next part is probably going to be confusing. But what you do is you put this into, this is the standard form for a differential equation. Okay? So we have the derivative plus a function of y equals a function of t times y is equal to a function of t. So in other words, the y, the term with the y in it, we need to move it to the other side. Okay? So I'm going to have dy dt equals, so 45y over 2000 minus 5t equals, and then just leave the 80. So what I did from this first step to this one is I just brought this one over, and then I keep the y out. Because when we identify the p of t and the q of t, or p of x and q of x, over here, it's this function without the y. So that's why you kind of leave the y separate. And so this is the p of t, 45 over 2000 minus 5t. And then the q of t is 80. So now I'm using the process that we did yesterday to solve these. All right, next I find the v of t. So the v of t is e, this is called the integrating factor. So the integrating factor is e raised to the integral of p of t dt. So here's the p of t. So that's a pretty complicated integral there. V of t equals e raised to the integral of 45 over 2000 minus 5t. All right, so over here, I just work on that. So here, I factor out a 5 and cancel with the 45. And then I bring the 9 out front. So let's see, where did, so when I factored out a 9, I actually factored out a negative 9. Can anybody tell me why did I bring out a negative 9 and left a negative 1 here in the top? Why would I want that negative 1 up there? Well, see, the derivative of 400 minus t is negative 1 dt. So that integral, when I have something, so this integral is going to be the natural log of the absolute value of 400 minus t. But so the derivative of it, I needed that negative 1 up there. So that's why I brought out the negative 9. Okay? So then so I put that here. And now I want to rewrite it so that the e is next to the natural log. So I'm going to have e to the natural log of the absolute value of 400 minus t times negative 9. That way, my e and my natural log are going to cancel, bringing this part down. And so I'll get 400 minus t to the minus 9 power. All right? Now, where did the absolute value signs go? Well, so in the problem, I'm only going to, the 400 minus t, see, t is going to be less than 400 because I'm losing 5 gallons per minute. And so after 400 minutes, I wouldn't have anything left. So this has to be positive, so I can drop the absolute value signs. Okay? So that's the v of t. So now the answer, the y, okay, this is the formula, again, another formula from yesterday. So y equals 1 divided by v of x times the integral of v of x, q of x, dx. So this gives us 1 over 400 minus t to the minus 9 times the integral of 400 minus t to the minus 9 times 80 dt. Okay, now using the elevator rule, I can bring this up and just make it 400 minus t to the 9th. and then bringing the 80 in front of the integral, I can take the integral 400 minus t to the minus 9, add 1 to that power, and then divide by that new power. And then I also have to divide by -1 because that's the derivative of this inside part, plus c. All right, so let's see. Now, what did I do here? I factored out a... 400 minus t to the 9th times 400 minus t to the minus 8. When you multiply here, you add the exponent, so you just get 400 minus t to the 1st. So those almost cancel. And then 8 will go into 80 10 times, plus, and then you have to distribute this to the c. So 400 minus t to the 9th times c. Then if I distribute, I get 4,000 minus 10t plus 400 minus t to the 9th times c. So that's the solution. Now, the only thing I have yet to determine is what the c is. So if you're, again, from yesterday, to find the c, you plug in the initial condition. And so the initial condition was, so that's the general solution. But then the initial condition is when t is 0, we have 100 pounds of stuff in there. So we plug in 0 for t and 100 for y. So that gives us 100 equals 4,000 minus 10 times 0 plus 400 minus 0 to the 9th times c. All right, so that's going to get us negative 3,900 equals 400 to the 9th times c. And when I divide by 400 to the 9th, that's going to be a really small number. That's pretty close to 0, but I still want to use it since I found it. So then my particular solution, so I take the answer where c was in my general solution and I plug that value in right here. That's what c was, and I plug that in, and that's the particular solution. And then finally I can answer any questions about it. So after 20 minutes, how much stuff is in it? What's the y? So then you plug in 20 for t here and here, and then that's just a calculator problem. So you plug in 20 for t, and then you get 1,342.027 pounds. So that's how much of the additive is in there after 20 minutes. Okay.